All right, so first thing, just to remind you, I mentioned this yesterday, beginning of class, as far as our next test coming up. I said yesterday it'd be Monday or Tuesday of next week, and that we'd know for sure later this week, and should know for sure after tomorrow. Right now, I'm kind of thinking it's most likely will be Monday. But so definitely keep that on your radar. That test three most likely coming up Monday. That'd be the 20th. But we'll confirm that tomorrow for sure, one way or the other. All right. So the last couple of I reckon classes we've been talking about beams and when we bend a beam, we apply a bending moment. It results in a normal stress. And we came up with a formula for the normal stress equals minus my over I, and we did examples yesterday. So today we're going to change gears and shift our focus toward shear stress that occurs in beams when they get bent. And this may not be quite as intuitive as the normal stress that occurs when you bend a beam, but it does occur, and that's what we're going to talk about today. All right. So, any questions before we get started? Okay. All right. So let's start with we got a beam that's being bent. So we'll try to draw this deformed bent beam here. So we apply a moment. All right, it's going to cause this beam to deform, bend, and we saw previously if we cut this and we look at cross section here where we cut it, we saw that there's a surface where the stress is zero that separates tension and compression. For a moment applied in this direction, right, it's causing the top to be in compression, right? So up here we'll have compression. Anywhere below that neutral surface we have tension. And we saw this normal stress is linear. So we're going to have, again, this is from sigma's minus my over I, y being vertical direction. So it's a linear relationship. The maximum compressive stress would occur at that top surface. Again, we're going on the assumption we're bending it this way. And we'd have tensile stress down here below the neutral surface. Our maximum tensile stress would occur at that bottom. Right? But we also know, right, sigma P over A, so we get the equivalent force by taking stress times area. So there's going to be a compressive force, we'll call it FC, associated with that compressive stress. There's going to be a tensile force associated with that tensile stress. Again, force equals stress times. Oops, sorry about that. Okay. All right. So basically, what we get, right, if you look at this cross section, right, we've got an equivalent force, in this case acting to the left, and we're below the neutral surface, we've got a equivalent force acting to the right. Right, well, that's going to cause a shear stress along that surface. We've got one force acting this way, one force acting that way, so it's going to result in a shear stress along that surface. Now, I started with this because this may be a little more intuitive how we actually get these shear stresses along that longitudinal surface. But what might definitely not be as intuitive is that this doesn't just occur at the neutral surface. If you pick any surface, longitudinal surface down this beam, we're going to get a difference in forces, excluding obviously the top surface and the bottom surface. Right? The top surface doesn't have anything above it. The bottom surface doesn't have anything below it. So we're not going to get the shear stress on that top and bottom surface. And we'll see this later when we derive this formula. Shear stress is going to be 0 along the top and the bottom surface, but any other surface, the shear stress is not going to be 0. Right? So I'm going to draw a different picture, a new picture. I don't want to get that one too cluttered. All right, so let's again say this is our neutral surface. And let's just look at this normal stress up here above the neutral surface. All right, again, this would be our maximum. All right, but let's take some other arbitrary surface here. All right, so let's look at what happens along that surface. All right, well, we're going to get an equivalent force, I'll call it FC. If we just look at this part of our normal stress, we're going to get a different force if we just look at this surface. I'll call it FC prime. Well, if again, force is stress times area, so the stress is larger here than it is here. So this force FC is going to be bigger than this one. So while they're still both going in the same direction, one's bigger than the other one. So there's going to be a difference in these two forces, and that's going to result in this shear stress that's going to act along that surface. Think about it like this. Just say, for example, say I got this. Here's our neutral surface. So say we're looking at these two. So maybe the force here is, I don't know, 10. The force acting there, call it F prime, maybe is 6. So in between those two layers, if you will, there's a difference in force. Well, we know this is in equilibrium, so the only way that the forces would add up to 0 is there's got to be an additional force acting, actually, this way, right, so that the forces add up to 0. Right? If you got two different forces, and that's where the shear stress comes in. We're going to get a force related to that shear stress. Just like there's a force associated with the normal stress, stress times area, there's going to be a force here, shear stress times area. And that's going to cancel out the forces, and we're in equilibrium. So our goal today is to try to come up with a formula for that shear stress. Right? So that's our goal. So let's look at a new picture here. I'm going to draw a new beam. Again, this is our neutral surface. let's we'll cut it somewhere here, and let's look at this part of the beam here. So this is going to be some distance, we'll call it y prime, away from the neutral surface. Remember, y is our vertical direction. So if we go some distance y prime above our neutral surface, and we want to look at this layer here. So there's going to be a force, call it P. And again, this is, we're still going on assumption we're bending it this way. So we have a compressive force above the neutral surface. And then we're going to have the shear force, or Fs. That's the shear force acting along that surface at that distance y prime. So again, P here is our axial force due to our normal stress. So again, P sigma times the area. What I call Fs is my shear force due to the shear stress tau. So it would be shear stress times whatever area it acts over. I'll just call it AS. Now I know this thing's in equilibrium, so the force has got to be zero. So whatever this compressive force P and the shear force Fs, they got to be equal. Now, if we look at the cross section, we'll draw a picture of the cross section here. So if we cut it here and we're looking at that cross section, again, the x-axis will be coming straight out the paper at you. This is our z-axis, or our neutral axis, the horizontal. And remember, it goes through the centroid of that cross section. So what we're looking at is this area that's some distance, forget the y bar, we don't need that yet, just y prime. All right, so that's what we're looking at. This area, the surface area for that cross section above y prime, we're going to call that A prime. All right. And what we're going to do is look at some little differential area, I'll call it dA prime. So when you're looking at that cross-section of the beam, that area above this distance y prime, we're denoting with A prime. And we're going to break it up into infinitely many little pieces of differential area. We'll call it dA prime. So I know the differential force dP, we'll call it, is whatever the normal stress is times that differential area. I call it dA prime. So if we want to get what the total force P is acting on that surface, pushing, in this case, pushing in, we just integrate. So this would be the integral over that area A prime of sigma times dA, or dA prime. But here's where we're going to use what we know, well, from previously. I know sigma, normal stress, is minus my over I. So we're going to substitute that in here. And we get, I'm going to pull the m and the I out. Right, so just substituting my over I in here for the normal stress sigma. Again, the moment and I don't vary over A prime. The only thing that does is y. So we have to leave that inside the integral. But this integral is equal to what we call q. So we're introducing a new term or new notation. What this is, it's the first moment of area A prime about the neutral axis. Now we're going to come back after we get our formula for shear stress, and we're gonna talk some more about Q, because my experience has been this is one of the most common things, places where students make mistakes, struggle, and so we're going to come back and talk about Q. But for right now, again, think a moment of inertia is a lot of times called the second moment of area, and reason for that is because I is the integral of y squared dA. Q, instead of y squared, is just y. And we'll see how we calculate it here shortly. But rest assured, just like we're not going to have to do any integration. We'll just be able to do a finite sum. But for now, just bear with me, and let's call this integral Q. So we're going to get P is equal to minus M Q over I. All right, so we're getting there. We've got expression now that we can get what that force is due to that bending moment. And now we need to do a little bit more to get to where we want to get to. Because, again, we're going to use this. That I know that shear force is equal to P. And now we know what P is equal to. And I need to draw a new picture. But I'm getting close to the bottom of this sheet. So I think I'm going to start on a new page. So if somebody needs another minute, a few seconds to finish writing anything down, speak up before I go to a new sheet. All right, nobody say anything, so we'll turn the page. All right, so and I'm gonna do my best here. We'll see if I can draw a slightly different picture, attempting to draw basically a 3D picture of our beam that we're bending. We'll see how it turns out. So again, same beam, bending it this way. But now we're going to look at a little bit different. Instead of looking at this longitudinal layer, what if we look at this little slice? If we somehow maybe I'll make these so basically we're going to look at this little slice across the beam where, say, at this point it's got some width t and length dx, some little infinitely small length dx. Now what I want to do is come down here and I'm going to draw a bigger picture of this. It's kind of a 2D. So let's go. Yeah, that won't work. Everything in 3D. All right, so here's my neutral surface. Yeah, well, I'll try. We'll see. If you look down the side, say if this was our neutral surface, again, we're some distance y prime above that. So this would be the end of this little rectangular slice that we're looking at here. So this distance is dx. And again, in 3D, it would go back this way, some distance t, right? But we're just looking at the end of this thing. And so we've got this differential force, we'll call it dP, and this differential shear force called DFS, right? Now, I saw on the previous, P was, the magnitude of P was mq over I. So we'll go back, the differential force would be Q over I times the differential moment. Now, our differential shear force is equal to whatever the shear stress is times the surface area that shear stress is acting over. Now, in this case, the area that this shear stress is acting over, it would be the bottom of this little rectangular slice, and this is where my 3D picture. I could real easy do it, show you the top surface, but it's that area, but it's on the bottom. So it would be that area along the bottom. Well, that area, right, it's a rectangle. It's t times dx. And I know, again, if it's in equilibrium, I know that shear force has got to be equal to the force due to the normal stress. So I just set these two equal to each other. So we got tau times t times dx is equal to q over I times dm. And we solve for tau. So we're going to get q over it and then dm dx. But now, if you go back and look in our notes when we started chapter 6, and we were talking about how to draw shear moment diagrams graphically, we came up with this relationship that V was dm dx. Shear was the derivative of the moment. That's how we knew the moment diagram was 1 degree higher than the shear diagram. If the shear was constant, the moment was linear. If the shear was linear, the moment was quadratic. So this is just equal to the shear force. So what we wind up with then is this formula, tau is equal to VQ over IT. That's the formula we're after and we're going to use to calculate shear stress. Now I want to go through and write out in detail what each of these terms are, so make sure everybody understands exactly what this formula represents. So maybe I'll do that. It's probably a good time to do that right now. So tau here obviously is the shear stress at a distance y prime from the neutral axis. V is exactly what it's been since day one. it would be the internal transverse shear force. On a cross section. So back in the first section, when we cut it and we found, I think I don't remember, we called it N, V, and M. It's V. We draw a shear moment diagram. This is V. That's what the V is in this formula. Again, Q again is the first moment area A prime about the neutral axis, where A prime here is the area above Y prime. So Q is just going to be the sum of A prime times Y bar prime. Now I need my Y bar. So when we look at the cross section, so again, just some arbitrary cross section of the beam, the x-axis coming right at us. This neutral axis, again, goes through the centroid. So we're calculating the stress. I did it again. Just Y prime. So this shear stress formula is going to give you the shear stress at this point on the cross section. The area above that is A prime. I'm going to call C prime. Is the centroid of that area A prime. And that's how we're going to calculate Q. Is we're going to take that area A prime, multiply times the distance to its centroid. That's what Q is. I is the moment of inertia for the entire cross-sectional area about the neutral axis. This is the moment of inertia for the entire cross-sectional area about the neutral axis. And we got one more T. T would be the width of the cross section. At Y prime. So whatever you come up here some distance Y prime, whatever the width or the thickness is at Y prime, that's the T that goes in this formula. All right, so stop a second. There's a bunch to digest there. Questions about, again, and keep in mind, just a minute, we're fixing to talk about Q some more. But so maybe other than Q, any questions about, what this formula represents? Any of those terms that go in there? Now, one thing that might not, again, be on your mind or thought about that much, but what we actually did, the way we derived this formula, what we actually came up with was what was the longitudinal shear stress. Right? What was the shear stress longitudinally down the beam? But it turns out this is actually the same as the shear stress on the cross-sectional surface area as well. So what we actually derived was the longitudinal shear stress. So if you look at some little element. What we actually derive this formula for tau there, again, this in the longitudinal direction, we actually derive that shear stress. But equilibrium says that for this to be an equilibrium, there must be, in addition to that, there's got to be a shear stress acting on this surface. We'll call it tau prime. Tau is equal to tau prime. Otherwise, the moments would not add to zero. Right? If you cut this little cube, this little element out of that beam, forces got to add to zero, the moments have to add to zero. Well, if these two shear stresses are equal, then the forces associated with that shear stress, again, force would be stress times area, those would add to zero. But the moment would not. What you actually would have is a couple. Right? This thing would want to rotate like that. So you've got to have something causing a moment in the opposite direction so that the moments add up to zero. Well, the only way that happens is the shear stress on those two surfaces have to be equal to the longitudinal. So the transverse shear stress is equal to the longitudinal shear stress. Anyway, just FYI, if you may or may not have considered that or thought about it, but I just wanted to point that out. All right. So now, before we actually get into solving a beam, again, I wanted to take a few minutes and let's talk about how to calculate Q. Maybe we'll just go through and do an example, put some numbers in here, and calculate Q, because it's by far and away that's where the mistake gets made more often than not. You've calculated moment of inertia a lot by now, and so you still make mistakes there, but not as many as you do with Q. And I always find it a little interesting because Q is actually easier to calculate than I. It's less work, it's easier, it's less to do. So it should be easier and you should make less mistakes. But invariably, I see the opposite. I see more mistakes made calculating Q. So that's what we're going to look at now. We'll look at a cross section. We'll put some numbers on it, and we'll practice calculating Q at a couple of places. All right. Speak up if you need a second. All right. So let's just look at a cross section. Let's do. Here we got a beam, got C section here, and this is supposed to be symmetric. We'll see. Mine may not come out to be too symmetric. Sure, it won't be to scale. All right. So say we got this cross section. Looks like a C, 16 inches tall. Commonly referred to as a C-section if you're identifying beams. Let's make it, say, 10 inches wide. And again, symmetric. The top and the bottom, they're the same width. Same thing for these. This is 2 inches. This is supposed to be 2 inches. And the width here is also 2 inches. All right, so if this is what my cross section looks like. So first thing we would need to do is locate where the centroid is, because that's where my neutral axis is located. Well, that we can get just from symmetry. The fact that this thing is symmetric. Right? Now, as far as the horizontal location of the centroid, that you would have to calculate, but we don't need it. right? This is my neutral axis. I know it goes through the centroid, but I know the vertical location just from symmetry. If this is 16, that's would be 12, so this would be 6 inches. This would be 6 inches. Right, my neutral axis is going to go right through the center of this thing due to symmetry. And again, the horizontal location of the centroid we don't need. We don't care about because we don't need that. What I need to know is where the vertical location of that neutral axis is, and so that we can get just from symmetry. All right. So say we want to calculate Q at the neutral axis. All right. So if we want to find Q at the neutral axis, all right, all we're looking at is the area above. Now, I didn't mention this when we were defining those terms of Q. I said it was all the area above, where your y prime. You could actually do all the area below y prime, and you would get the same number. You would get a negative. So sometimes if it's a lot less work to do the area below y prime, you can do that. Just remember you're actually going to get a negative number, but just disregard the negative, and that would be equal to a Q for all the area above y prime. But in this case, it's the same amount of work either way. Above, below, it's the same. But all we're going to look at is the area above the neutral axis. So here we would have, again, we're not going to have to integrate anything. We're going to be able to break it up into almost always a combination of rectangles. But certainly nothing that we would have to integrate. So here's my neutral axis. And again, remember Q is the sum of the area A prime times y bar prime. So here A prime would be all the area above that. But we can break it up into two rectangles. And you could do this two different ways. We could break that way or this way, and maybe I'll go this way. Right, so I'll call this A prime 1, and we'll call this one A prime 2. So to get Q here at the neutral axis, I take A prime 1 and multiply times the distance to its centroid. So we'll call C prime 1 centroid there. This would be Y bar prime 1. Lots of subscripts and superscripts and things. But that's how we calculate Q. We take this area, multiply times the distance to the centroid. And then we do the same thing for area A prime 2 up here. Take its area, A prime 2, and multiply times the distance to its centroid. It's essentially, if you think about, when you do moments of inertia and you use a parallel axis theorem, you have to add AD squared. Well, here, Q is just AD. That's it. That's all it is. So if you can calculate I, where, say if it was a rectangle, we'd have to do 1/12 base times height cubed plus AD squared. Well, Q is just AD. That's it. So if you can do I, you should be able to do Q. It's easier. It's less work. So that's all we got to do is just add up the area times the distance. Now, this is 6 inches. This is 2 inches. This is 2 inches. And this is 10 inches. All right, so A prime 1 is just this area. 6 times 2 is 12. Right, and the distance to this centroid would be half of 6, 3. A prime 2, this area, 10 times 2 would be 20. And the distance to its centroid, we go up 6, and then half of 2 is 1, that would be 7. Right? And then we add those up. 36 and 140 is 176. Now these would be inches cubed. Again, units here are going to always be length cubed. That's it. That would be Q at the neutral axis. So if we were finding the shear stress at the neutral axis, this is what we would plug in that formula for Q. All right. Any questions how we calculated Q at the neutral axis? All right. Well, let's do one more location. Say we wanted to, if we wanted to find what the shear stress was here. Right, when we use that formula, VQ over IT, if we want to know what the shear stress is at this location on that cross section, we use Q at that location on the cross section. So to find, see what Q at that location, we just use the area above that. So again, here's A. So in this case, if we want to find QAA, we just use this area. This would be A prime. This would be Y bar prime. What you see, it's the same as what up here was A prime 2. And so this would just be A prime times Y bar prime, which would be 20 times 7, 140 inches cubed. Again, this was 10 inches by 2 inches. And this was 6 inches. Right? So that's what we use for Q if we're calculating the shear stress at that point on the cross section. Q is just all the area above that times the distance to the centroid. And so you see, is looking at this, Q max is going to be at the neutral axis. Right? That's where you're going to get your largest Q because you're using all the area above the neutral axis. If you go some distance away from the neutral axis, like A here, right, we're not only using the area above that, we're going to get Q, it's going to be smaller than it is at the neutral axis. And so that's an important observation here. Q max is at the neutral axis. That's where you're going to get your largest Q. And that kind of leads us into how we know where the maximum shear stress occurs. Right? All right, any other question about Q at this point? Tomorrow we're going to go through and work a whole problem where we do shear stress, and we'll obviously have to calculate Q again. But at this point, questions about how to calculate Q? All right, so we got about 5 minutes left. So again, we're not going to have time to go through and work a problem, but I want to take the last 5 minutes and talk about this formula and how we know where the maximum shear stress occurs. Well, from what we just talked about, Q would be 0 at the top and bottom surface. Right? Remember, we said Q is all the area above that. Well, there is no area above the top surface. There is no area below the bottom surface. So Q is 0. So shear stress is going to be 0 at the top and bottom surface will be lazy, right? Which is exact opposite of the bending stress. Now, the bending stress was 0 at the neutral axis, and its maximum was at the top and the bottom surface. But shear stress is going to be 0 at the top and the bottom surface. Now, the actual maximum occurs at tau max. V and I are constant with respect to the cross section. Right? The shear force V is the shear force acting on that entire cross section. I is the moment of inertia of the entire cross section. What changes if you move to a different point on the cross section is obviously Q and possibly T. So it's going to occur where this ratio, Q over T, is a maximum. Right, that's where you're going to get your maximum shear stress. Well, we know Q is a maximum at the neutral axis, right? So that's going to give me the largest numerator. So if I can get the largest numerator and the smallest denominator, that's going to give me the largest value. So if the minimum thickness is at the neutral axis, tau max is at the neutral axis. And this is what's going to occur the vast majority of the time. And that's the first thing you should look at, is the minimum thickness at the neutral axis. If the answer is yes, then I know that is where my maximum shear stress is. Again, it's the opposite of bending stress. Bending stress was 0 at the neutral axis. Most of the time, that's where our maximum shear stress occurs. Right? So just for example, if you got one of the most common shaped cross sections for a beam is an I-beam. Well, this would be the thickness at the neutral axis is the minimum, right? So for an I-beam, or any beam like this where the minimum thickness is the thickness at the neutral axis, that's where you're going to get tau max, is the shear stress at the neutral axis. Now, most beams, this will be the case, but now it is possible, last thing I wanted to mention, is that it is possible that the maximum shear stress does not occur at the neutral axis. And for those, you can't necessarily just look at it and tell. Say, for example, if we take this I-beam and turn it over and make an H-beam out of it. Let's go this way. Let's do it there. All right, so here's my neutral axis. Well, typically, this would be called H, the height of the I-beam. This would be the thickness of the flange. So the question now becomes, let's say, instead of neutral axis, what if we go just above there, and I don't know, we'll call this AA again. So is Q over T at the neutral axis, is that larger than Q over T there? I don't know. I can't look at it and tell you the answer. Because, yeah, Q, remember, is always largest at the neutral axis. So, yeah, Q here would definitely be larger than Q. But it's not going to be a huge difference, right? Because we're not, we're not losing a whole lot of area, right? The area above AA is less than it is at the neutral axis. So it's going to be less, but not significant, not a huge difference. But look at the thickness at the neutral axis, right? That is much, much greater than the thickness here at AA. Here, it would be H, that entire width. Here, it would just be 2 times the thickness of the flange. So this thickness here is a whole lot less than the thickness there. And so you very likely could get a larger shear stress here at AA as opposed to the neutral axis. But the only way to know would be to calculate it, right? Now, again, this is not going to happen very often. You don't see I-beams turn like this for a reason. The moment of inertia is a lot less. You got a weaker beam. Sigma is equal to, my over I. So the larger the I, the lower the stress. Well, I here for the I-beam is much, much greater than it is for an H-beam. So that's why you don't see I-beams turn this way. It's a stronger beam. That's the whole purpose in an I-beam having a cross-section like this. You increase the moment of inertia by moving the area away from the axis. That's the motivation for having an I-shaped beam. But, for whatever reason, some special circumstance, you could run into a beam like this. But not very often, right? So always just check first. Is the minimum thickness at the neutral axis? Yes, I know that's where the maximum shear stress is. And that's what you'll find almost all the time. But I did want to mention it's possible to not be at the neutral axis. All right, so that's where we're stopping. We're going to apply this tomorrow and see if we can calculate, what the maximum shear stress is in a beam. So I'm stopping recording, and again, if somebody has questions they want to stick around and ask, I'll be glad to do so. So give me just a minute to stop recording.